You're absolutely right. I forgot. Thank you. Thank you for reminding me. Sorry about that. You lost the first 12 minutes, but I was just trying to scare you with the exam. So I've only been talking about deflections for about 5 minutes. Anyway, thank you for reminding me. Okay. So from the previous example, the total deflection, this was long-term dead load plus live load, was 4.39 inches, minus the immediate deflection due to dead load was 1.063 inches, leaving you with 3.33 inches of movement after the building's been complete. Your allowable is L over 240, which is 36 feet, and then you convert from feet to inches over 240, and your allowable is 1.8 inches. So 3.3 is quite a bit more than 1.8. The deflections are unacceptable. You also check live load deflection. So we found from the previous example that our delta live load, the deflection due to live load only, was 1.11 inches. It must be less than L over 360, which is 36 times 12 over 360 is 1.2 inches. So the beam actually passes for live load, but not for total load. Okay, so let's go back here a second. The same question that I asked last time. This number is bigger than this number, so this is unacceptable. What could we do to fix this?
Make it shorter.
That's one way. Make the beam shorter so you'll have less deflection. Absolutely. What else could we do?
The type of materials.
Make the material stronger.
Yeah.
That is true, but remember what we talked about last time, that the modulus of elasticity is based on the square root of F prime C. So yes, you could go from 4,000, 5,000 to 6,000 PSI concrete. Problem is it doesn't get you a whole lot because of that square root deal in there. What else? What else can we do?
The dimension.
I'm sorry, the what?
The measurements.
We can change the section properties.
Yeah.
Yep, that's probably the most effective. Basically make the beam deeper. That because your section properties is based on I gross and I cracked. I grossed and I cracked are based on the moment of inertia of the beam. The moment of inertia of a beam, a rectangle, is BH cubed over 12. So making B bigger doesn't help you a whole lot, but a little bit deeper on the H adds a lot because of that cubic function. So that's probably the most effective, is to make the beam deeper. Okay, any questions on this?
So that's the first thing that you're gonna change if you want the deflection to become smaller.
Is to make the beam deeper. Yes,
Yes.
yes. But
Before you touch the other, like the length and then the type of materials.
possibly, possibly. The materials is a lot more expensive way to control deflection because going from 4,000 to 6,000 is quite a bit of increase in cost over thousands of cubic yards in a building. And it doesn't get you very much. But adding a few inches is just like a percentage of the concrete you already are going to provide. So if you had like a 30-inch beam to go to a 34 or 36-inch beam, is you're buying more material? Yes, but it's the most cost-effective way to do it. The only problem with making the beam deeper is you have to talk to the architect and make sure that you can make the beam deeper. That's where you run into architectural constraints. Okay. Cracking. All right. How many of you currently are aware that pretty much all reinforced concrete cracks? Okay. Now, most of you are aware that concrete, reinforced concrete always cracks. Ooh, blue hands. I like that. Cracks are an acceptable, or unless you're raising your hand, is that to say yes, or you're raising your hand to talk?
To say yes.
Okay, cool. Cracks are an acceptable fact of life with reinforced concrete. Steel reinforcing doesn't even start to work until the concrete has cracked, right? So reinforced concrete cracks. That's what it does. If you have floors or a slab, then they generally are going to crack because they're trying to shrink and they're restrained. They're not allowed to shrink. So you're going to get cracks in your floor. You're going to get cracks in your driveway. You're going to get cracks on your warehouse floor. It's inevitable. What we do for floors and slabs is we put in control joints on a regular pattern to try to control the cracking so that it doesn't look ugly. The cracks are placed in the control joints so they're controlled. And then we provide a minimum amount of steel. As we learned in our one-way slabs, we put a minimum amount of steel so that the cracks, again, are controlled. Cracks in beams, though, are different. Cracks in beams, you're going to get cracks in beams basically from flexural action. As we've been talking about all along, is that the tensile stress in a typical reinforced concrete beam is going to far exceed the concrete's ability to resist tension. So pretty much all reinforced concrete beams are going to have cracks. The thing is, the cracks should not be noticeable. If you go to any reinforced concrete project and look really closely at the beams, look at the bottom of the beam, at the midspan of the beam, you might see what we call hairline cracks, just little teeny cracks. And sometimes you really got to look for them. Well, that means somebody did their job. They controlled those cracks, but you can't get rid of them. There's always going to be cracking. So that's the name of the game. That's what we're trying to do here. We are simply trying to control cracks so that they are architecturally acceptable and they would not be disconcerting or worrisome, causing fear of people who are using the building. So that's the main reason to control your cracking. So cracks cannot be avoided. They must simply be controlled. ACI 318 no longer explicitly limits the crack widths of reinforced concrete. They put a limit on reinforcing spacing, right? But they don't put a limit on the actual crack width, like in thousandths of an inch, how wide the crack can be. They used to use as a guide the following values. Okay, so we had exposure categories, we had an allowable crack width. For dry air or a protective membrane, you could go up to 16 thousandths of an inch as a crack width. Just to kind of give you an idea, the thickness of this font here, at least as it is, as I'm looking at it, let's see. Oh, sorry, hold on a second. still have this thing. Aha! Okay. If you guys are still able to see me, I am holding up my crack comparator. And I'm not even sure that's really a word, but that's what it says right here on this little piece of plastic. It says a crack comparator. And if I put my crack comparator on, say, the L's in the allowable right here, that is right about there. Okay, so the thickness of the vertical line of the L in this allowable right there is 20 thousandths of an inch. So the thickness of that L, at least on my screen, is already beyond the allowable crack width for dry air or a protective membrane. Okay, does that make sense? What I did was I used this card and it has different thicknesses of lines on it, and you lay that card over your crack that you are concerned about, and you compare it to these numbers on the side here, and that will tell you how approximately how wide the crack is that you're looking at. If we are in humidity, moist air, or soil, then your allowable crack width is only 12 thousandths of an inch. If we are near de-icing chemicals, which is really, really nasty to rebar, you want to keep those cracks even less at 0.007 inches. And if you are exposed to seawater, seawater spray, or wetting and drying cycles, you want to keep it under 6 thousandths of an inch. Water retaining structures, concrete water tanks, basically, you want to keep them to 4 thousandths. So these are just some expressions. Now the code used to actually have this in the code. The 12 thousandths and the 16 thousandths were kind of built into the code equations. Those equations are all gone. I'm not sure why, but somewhere around 2002 or so, they eliminated those expressions, and I'll show you what they put in. But what they used to have is still really useful to check your crack widths. So this is what they used to have. 0.076 beta H f sub s to the third root of dc times A. This was known as the Gergely-Lutz equation. Gerge. That's why I put that there. Okay, because I mess it up every year. It's the Gerge-Lutz equation. So funny, I had to put that in there because I just keep doing it. Where W is a crack width in thousandths of an inch. So the number that you get is thousandths of an inch. Beta H is the ratio of distance from the neutral axis to the extreme concrete in tension over the distance from the neutral axis to the tension steel. F sub s is the stress in the steel in KSI. The code used to say that the user may use 60% of the yield for simplicity, but since we learned how to calculate what that stress is, you can calculate that stress and use the more accurate value. D sub C is the cover of the tension steel from the centroid of the steel to the extreme concrete in tension. And A is the effective tension area of concrete, equal to the area of the concrete with the same centroid as the steel, then divided by the number of bars. And yes, I'll have an example showing you how to use these.
Professor?
Yeah.
So do we not use the table with the exposure categories anymore? Is that just showing like what you guys used to use in the code? So we only use this equation that was given?
Okay, so this equation is not in the code anymore, but that doesn't say that we can't use it. It's just not mandated by the code. So if you use this equation, it's going to give you a number. that number is going to be thousandths of an inch. It could be 17, it could be 2, it could be 5, whatever. Well, if you use this equation and you get a number, what does that tell you? I don't know. What if the number's 20? Is that okay? What if the number's 10? Is that okay? So you have to have this acceptance criteria that I outlined here as something to compare to the number that you get out of this equation.
I see. That makes sense. Thank you.
Okay. All right, so here's our example. Same beam, 20 inches wide, 27 inches deep, 6 number 8 rebar. And we want to repeat example number 1 to find the maximum crack width with the dead load only. From example 1, we know that the beam is cracked under full loading. Therefore, we use the crack moment of inertia. Okay, so we're going to use the modular ratio is 29,000 over 3605 is the modulus elasticity of the concrete and the modulus elasticity of the steel. That's 8.04. Y sub B is 19.06. That's the distance from the bottom of the beam to the neutral axis. We got that from example 1 last time. The cracked moment of inertia is 13,788. We got that last time. And MA in this case is going to be the dead load because the problem stated find the maximum crack width with dead load only, which was 253.2 kip feet. All right, so now this is all from example 1. Now we're moving into example 5. F sub S. F sub S, remember, is the stress in the steel. F sub Y is the yielding stress. F sub S is the actual stress due to this load 253.2. So stress is equal to My over I, the flexural equation. So you have M is Ma, Y is YB, and I is I cracked. And then don't forget you need to multiply by the modular ratio N, because we transformed all the steel into concrete so that we could find the moment of inertia, apples to apples, but it's still steel. So you have to transform it back to steel when you're getting your stresses. So I put into 253.2 kip feet. I translate that or convert that to inches times my neutral axis times my modular ratio divided by my crack moment of inertia, and I get 33.8 KSI. So theoretically, that's the stress in the steel under this load. Beta H is the ratio of the distance from the bottom to the neutral axis divided by the distance from the centroid of the steel to the neutral axis. So that's 1906 over 1906 minus 2.5 because the steel is 2.5 inches up from the bottom. And that gives you 1.151. D sub C is the distance from the centroid of the steel to the bottom of the beam, which is given as 2.5 inches. A, the hatched area represents A. A is the tensile area of the concrete. So the hatched area has the same centroid as the steel. That's the key. So if the centroid of the steel is 2.5 inches up, then A has to be, or this area has to be 5 inches, so that the centroid of the red hatched square is the same as the centroid of the steel. So that gives us, and what I did here is the steel is D sub C up 2.5 inches. So A is twice that. So I have 2 times D sub C times the width of the beam over N gives me, and this is, I'm sorry, I used N twice, didn't I? N is the modular ratio here. Here, N just represents the number of bars. So what you're really looking for is the tensile area of concrete per bar. So you have 2 times 2.5, that's the 5 times 20 divided by 6 bars. And that gives me 16.67 inches squared per bar. What you'll notice from this expression, though, from this equation, is that if you have to provide a given area of steel, for crack control, it is better to use more smaller bars than less bigger bars. Okay, so you're going to get a much better crack control from 4 number 8s than you would from 2 number 11s, for instance. And that comes out in this equation. So my Gerke-Lutz equation, I plug in my beta H, my F sub S, my DC, and my A go into here. I crank it out, and I get 10.3. Well, what I get out of the equation actually is 10.3, but the equation tells you that that is thousandths of an inch. So I get 10.3 thousandths of an inch. And is that okay? Well, actually, I skipped ahead, didn't I? So is that okay or is that not okay? Typically, the table before illustrated that if you're in the ideal situation, inside or a dry atmosphere, then you can go to 16 thousandths. Otherwise, you want to keep it to 12 thousandths. Well, this calculated to be 10.3 thousandths, so either way, this is going to be okay for crack control. Any questions on example 5?
I have a question, Professor. So this A is the area per steel, right?
Per steel bar.
Steel bar, not the area of the hatch in the figures.
Well, it is. It's the area of the red hatch divided by the number of bars.
Okay.
So you can see here, I have 6 number 8s. So I divided by 6 to get you this number here. But instead of 6 number 8s, just as an example, 6 times 0.79 is 4.74 divided by 2, 2.37. How about 4.74 divided by 3? 1.58. That's really close to 3 number 11s. So instead of 6 number 8s, I'm getting really close if I use 3 number 11s. But if I use 3 number 11s, this equation doesn't care what size bar it is. It just wants to know how many bars. So this 6 would become a 3. So if this was 3, then this number would be 33 or so. It would double. So if you put 33 here, then what you would get, 2.5 times 16.67 times 2 to the 1/3 times 33.8 times 1.151 times 0.076, you get 12.9. So what I'm trying to say is 6 number 8s got us 10.3 thousandths. If I had used 3 number 11s instead of 6 number 8s, it's basically the same area of steel, but then my cracking index would be 12.9 thousandths instead of 10.3, which in many environments would not be working now. That crack is too wide. So just illustrating how using multiple bars controls cracking better.
Okay. So it's better to use more smaller steel to control the cracks than big steels, but lesser.
Yes.
Okay.
Yes. Within reason. Within reason. 6 number 8s is a good answer. That's totally buildable. You can even go, instead of 6 number 8s, 5 number 9s. That's okay. But what I'm saying is you don't want to go to just like 3 number 11s or 2 number 14 bars. That would not do a very good job with cracking. On the other end, 6 number 8s is very reasonable. I would not go to like 20 number 4s. That would be unreasonable.
Okay, and it's also depends on the measurements if we have constraints and whatnot, right?
Sure, sure.
Okay.
Yeah.
Okay, that makes sense.
Okay. All right, so that's what ACI used to do. And actually, this procedure is something that a lot of us in the industry still use, because this is actually much more helpful and meaningful to those of us trying to control cracking than what the code does today. But what the code does today is it now limits crack width by limiting the spacing of the flexural reinforcing bars. ACI section 24.3.2 points to table 24.3.2 that limits the spacing of reinforcement S to the lesser of S maximum is 15 times 40,000 over F sub S minus 2.5 C sub C, or 12 times 40,000 over F sub S. ACI section 24.3.2.1 allows F sub S to be calculated or to be taken as 2/3 of the yield stress. C sub C is the clear cover of reinforcement. This ACI 318 criteria is more useful for rebar spacing in slabs, like the homework assignment you guys just did, where you found that you need number 6 bar at 12 inches on center. This would be something to check the maximum spacing with of those rebars to be sure that you're not getting into a crack control problem. But for beams, not so helpful. Oh, that was the last slide. So let me show you why. For beams, you run this equation here. In fact, we can. Let's do 40,000 divided by, what did we have, 33,000? Times 12. And this gives me a maximum spacing of my rebar of 14.5 inches. Well, I got 6 number 8s in a 20-inch wide beam. My spacing is like 2.5, 3 inches. This is not helpful at all. So again, just a user, opinionated user. I've been using this code for 27 years, and this is complete poo-poo. It just is meaningless when you're trying to design beams. So just my opinion. Any questions about serviceability? Okay, all right. Let me take a few minutes to make some observations. I just finished grading homework number 3 yesterday morning, I believe. And so I noticed that after 3 homeworks, I'm still seeing some common misconceptions, I think. So things that I've noted on your homeworks, but I did it over and over and over. So there's a lot of you with the same direction, the same correction that needs to be made. So let me see if I can remember them all. First one is that if you're doing a flexural design, now we've already talked about shear, and now we've gotten into cracking and deflection. But if you're doing a flexural strength problem, whether it's a singly reinforced rectangular beam, or a doubly reinforced, or a T-beam, or a one-way slab, doesn't matter. If you're doing a flexural strength problem, you always need to check your minimum steel. You always need to check if epsilon sub t is greater than 0.005. which is your check for maximum steel. And you always need to check that VMN is greater than MU. The only exception to VMN greater than MU is if it's an analysis problem and you don't know what MU is. That's the only exception I can think of. I just throw a beam at you and say, all right, what's the capacity? Then you don't need to check it against MU, but obviously I'm asking for the capacity, so I need to know what MN is or VMN is. But a lot of you on the design problems went down the road of picking a D dimension and then figuring out how deep the beam is and then picking a steel and then done. I'm using 3 number 10s or 3 number 9s or whatever. And you didn't do the minimum steel check. You didn't do the maximum steel check. You didn't do the most important check, VMN greater than MU. Okay, so that's the first observation. Any questions on that?
Professor,
Yes.
can you repeat what you said about the capacity when you check MN and greater than U? When it's given or not given, what did you say?
Okay, if I give you a beam for an analysis problem, so everything about the beam is known, and I ask you, tell me the capacity of that beam, you need to calculate MN. And if I ask for the allowable capacity of that beam, you need to give me phi MN. But you don't actually check it against MU if I haven't given you any loading. Clearly, you can't show me that phi MN is greater than MU if I haven't told you anything about the loading. But if it's a design problem where I give you the loading and you have to choose the size of the steel or the number of the bars, whatever that is, then the last thing you always have to do is be sure that all the choices you made in the design phase gives you a beam where phi MN is greater than MU. Okay, so the last homework assignment, we had a few design problems on it, and many of you students did not do the phi MN greater than MU check based on your choices for those design problems.
So my second question is, when you are doing the design and you choose the bars and stuff,
yes.
For example, like I know in one of the homeworks, for example, I had 3 number 7 bars, for example, but a number say 3 number 8 bars still gives you that greater than when you check it. Like, do you want us to be the closest number to the allowable, or?
Yes. Yes.
Okay.
And you'll notice that hopefully I did this. Hopefully I was smart enough to do this, but in most cases, when I give you a design problem, I tell you use number 10s or use number 11s. I tell you what bar to use so that you can choose the number of that bar closest to the right answer. And in that way, everybody should have the same answer, right? If I didn't do that, then you could say, I'm using 24 number 4s. And your classmate will say, well, I'm using 16 number 5s. Oh yeah? Well, I'm using 3 number 10s. And you're all right. So I have to limit your choices.
Everything would just be over designed.
Well, okay. That's a second issue. That's a second issue. The first issue is I will tell you what bar I want you to use so that everybody gets to the same answer. The second issue is if 3 number 10s does the job, then if you tell me I want to use 4 number 10s, then that is wrong because that's not the most efficient answer. VMN will be greater than MU, but by too much. See what I'm saying? Do you not see what I'm saying?
Yeah, sorry.
All right. So no, that's a great question for everybody. That's a great question. If the solution is that 3 number 10s does the job with a VMN is greater than MU with 3 number 10s, then 3 number 10s is the right answer. If 3 number 10s is the right answer, 2 number 10s is not, nor is 4 or 5 number 10s. That's equally wrong. So having too much or too little is equally wrong. You should get to the same answer, 3 number 10s. Okay, the other thing that I noticed a lot of students doing, and maybe I didn't cover this clearly, but I want to talk about it now, is that in some design problems, you don't know the steel and you don't know how deep the beam is. So I gave you tools and techniques to derive based on the load that it's supposed to carry, how deep D needs to be. And for one example, one homework problem, D calced out to be 25.59. When you calculate it from the Rn is equal to mu over phi b d squared, when you calculate D, it was 25.59 inches. That's what I got. That's hopefully the right answer. But, and I wrote this on the number of your papers, but I just want to make sure everybody's on the same page. You cannot take 25.59 and round it up to 26. You can't do that. Because when you do that, you're saying, I want to build a beam where the distance from the top of the beam to the center of the steel is 26 inches. But when you add the 2.5 inches below the steel that you need for the beam, now you're asking the builders, the contractor, to build you a 28.5 inch deep beam. And they're not going to do that. It's going to cost them a ton of money to come up with custom forms like that. So that is not the procedure. You do not take your required D and round it up. What you do is you take your required D, add 2.5 inches to it for the cover to the center of the bar. So 25.59 plus 2.5 gives you 28.09. And then you, the designer, decide how deep the beam ought to be. Are you going to use a 28-inch deep beam or are you going to use a 30-inch deep beam? That's your decision. You can use a 32-inch deep beam if you wanted. That's your decision as a designer. But you have to choose a beam depth, right? So you don't round up D. You use the minimum D to find the minimum height of the beam, and then you choose a beam. Now, if I choose 30, then D is 30 minus 2.5 inches. Okay, do you see how you're bridging between the minimum required by the mathematical calculation and your choices as a designer? At some point, you need to choose how deep the beam's going to be, not D, but H, the depth of the beam. And what you choose is what you're going to ask the contractor to build. So you better make it an even module, 28, 30, 32, 34, 36, something like that. And once you choose the depth of the beam, then you calculate what D is based on your choice. The same thing applies to choosing steel. You can't use the area of steel that you got from row minimum, which was 9.26 inches squared or something like that. That's not a choice. That's just the minimum. You have to choose. Am I going to use 5 number 10s? Am I going to use 3 number 9s? Whatever the combination is that you choose, You have to make that choice. And once you have decided the depth of the beam and the steel that you're going to use, both of those are going to give you numbers different than the minimum required. So D minimum and the D that you build are different things. AS minimum and the steel that you choose are different things. That is why after you have chosen the height of the beam, which calculate the D, and chosen the steel, you need to always go back and check your minimum steel, your epsilon sub T greater than 0.005, and is VMN greater than MU. You have to make all those checks because you've made all these choices that may or may not pan out. All right, that was a long speech. Any questions about that topic?
I have a question about the professor. So in the homework, it has 2 rows, right?
The steel was in 2 rows?
Yeah,
Okay,
6
okay.
number 11s.
Oh, okay, okay.
And then you deduct me -1 point because you said that the D will change since I have 2 rows now.
Yes. Yes, I did. I remember your paper.
And
I did it with evil intent.
yeah, so is that the one that if I design this as 1 row, this would be right?
Okay. Let me draw a little figure because that's a great question and I want everybody to understand what we're talking about.
Okay.
So here's our beam. Okay. And if you have steel in 1 row, I'm going to try to make this pretty. Well, close enough. All right. And so in your case, and thank you for asking the question, but I'm going to use you as an example a little bit. In your case, you calculated D minimum. And let's just for conversation say that D minimum was 25.59. I'm not sure if it was that problem or not, but let's just say. So you did what I'm talking about. You took 25.59 plus 2.5. That's 28.09 inches. And then you said, okay, well, I'm going to build a 30-inch beam. So then the beam, by your choice, is 30 inches, which is totally cool. So this is 30. And then you said, well, D then is equal to 30 minus 2.5 inches, which is equal to 27.5 inches. Okay, cool. And then you sized your steel. But at some point, you realize that you can't fit all that steel in a single row. So then you did what anybody would do. And you went back here and you said, I need 6 number 11s. And they're going to be in 2 rows. Okay, no problem. No problem at all. Except what you forgot to do, and I wanted to just call this out to make sure that you understood what you forgot to do, is that you assumed a single row when you came up with these numbers. You took 25.59 plus 2.5 and then chose 30. And then you made D 30 minus 2.5, which is fine for a single row. But as soon as you realized, oh, I lost everything. Okay, hold on. Having technical issues here. There we go. Okay, so as soon as you, why can I not grab? That's frustrating. Mouse, grab. It won't let me grab it. Yeah, okay, so anyway, As soon as you realized that you needed 2 rows instead of 1, then you need to recognize that every time you use this 2.5 inches, that's not valid anymore. Because now the centroid of your 2 rows is 2.5 plus half a bar plus half an inch. If you use 3.5 inches, in my book, that's close enough. Or you can use 2.5 inches and actually calculate half of a number 11 and add a half inch to that. That's more accurate. But either way, you do it that way or just use 3.5, that's close enough. But you didn't recalculate D from your chosen 30. So when you went to 2 rows, either 30 gets deeper or you have to recalculate D is now equal to 30 minus 3.5 inches. So D is only 26.5 if you keep the 30. That's what the point was about.
Okay. Yeah, so it's either I shorten the D
Yes,
or longer the H.
yes, that is correct. Yeah.
Okay.
Now
Professor,
this,
do you take in consideration the 2 rows when you're finding, for because he had 25.59, I think you said, for the D min. Do you take
yes.
in consideration the 2 rows there or after?
Well, after, because he didn't realize that the area of steel precluded him from putting it in 1 row.
So when he adds, no, sorry, when he minuses the 2.5, he should have minus 3.5 instead of 2.5.
Yes,
Okay.
yes. But remember, design is an iterative process. So I would not have expected him to realize that he can't fit it all in a single row. But what I was looking for is once he did realize that you can't fit it in a single row, I would expect that you would go back and fine tune some of these assumptions. Okay, thank you. So it's an iterative process. We're picking on you, Adriel. We're just picking on you because you asked the question. But once he did the 30 was perfect. He did the 27.5, that's perfect. But then he realized I can't fit it all in 1 row. He needs to go back and revise D from 30 minus 3.5. And in this particular case, that would have got him 26.5. 26.5 is still more than the 25.59, so he would have been fine. He just needed to make that adjustment. If he had gone 30 minus 3.5 and it got to be less than the 25.59, then he probably would have to adjust his height from 30 to 32 to get it to still work. It's an iterative process. You just can't get around that. But that's what I was looking for, Adriel. I was just looking for recognition that this assumption was made invalid by your 2 rows so that you have to go back and make a little bit of a correction.
Okay, that makes sense. And I have one more question, Professor.
Okay.
So let's say your minimum, you have your minimum requirement for steel, right? I mean the AS required,
As required.
and then you find out that you need 5 bars, but you cannot fit it in 1 row. I have a odd number, like 3 at the bottom and 2 at the top. Is that fine or?
It is fine. Yes. You don't always have to provide even, but what's going to happen, I cannot, this is so frustrating. I can't, or I could do this. Okay, how about this? Doink. Okay, say that's your rebar. That's totally fine. But what you're going to find is that your center of gravity is not halfway between the 2 rows now. Now you actually have to calculate where your center of gravity is. It's going to be closer to the 3 than to the 2. So that's the only complication of using an odd number of bars.
Right. Okay. So, but hopefully you don't give us like that. But in our case, can we just like make it even so that I know that you're above the requirements. You're more than above the requirement, but it would be easier to find the center of gravity for that one.
Well,
The centroid for that one.
it depends. It depends. If I said use a certain size bar and the answer is 5 of those bars, then you got to use 5 of those bars and calculate where D is a little bit more accurately. But if I didn't tell you what size bar to use, then you could just go, instead of 5 number 10s, try 6 number 9s. And that would even it out as well.
Right. Okay, that makes sense.
Okay,
Okay. Thank you.
sure. Still got a question, Alejandro?
No, I'm just listening.
Okay, okay, no problem. I'm trying to remember the other comments that I had in the homework. I talked about rounding up D, which you do not do. You have to choose an H. I had quite a few students calculate row minimum or the, not minimum, the required steel based on the load. So like a row required or AS required. And they never actually picked a rebar pattern. So that's a big problem too. You have to choose. You can't just go with AS required. You have to choose a number and size of bars to complete your design. Let's see. I did mention, I'll mention it again. The test covers from day 1 until T-beams, but it does not include doubly reinforced beams. So the final is going to cover basically the whole semester, but it's going to, the final is going to be more like from doubly reinforced beams to the end of the semester, more of a focus there. This midterm does not include doubly reinforced, but it does include T-beams. Okay. Simon, are you with us? Your tablet died.
I have one more question, Professor.
Sure.
So for when you're looking at the minimum row, we can use the table, right? But sometimes I notice you give us like a formula if the Fy is greater than like more than 60 grade, and the FC is more than 5,000.
So the answer to your question is, if I want you to use the equations that I gave you instead of the tables, then I will give you an F prime C and or Fy that is not in the tables. I will give you the evil chuckle, and I'll say F prime C is 4,500. And then you can't use the tables. You have to use the equations.
Right. So we have to use the table because we can't find it on like, okay, that makes sense.
Okay. But listen for the evil chuckle. That's your cue.
Okay, that makes sense.
Okay. One other thing, I guess just some housekeeping. When you get into the test will have text boxes, and I am looking for answers in those text boxes. But you can't put all of your work in those text boxes. You're just going to put the answer that I'm looking for in the text boxes. So you're going to then submit your test through Blackboard, and then you're going to scan your 1 page of notes and all of your hand calculations that you did supporting your test. You're going to scan those, and you're going to scan them up to an assignment called midterm. It's just like a homework assignment, but it's going to be called midterm. And that way it's going to be worth 0 points, but it's to your benefit that I can grab as much partial credit for each problem as possible. So that's, you're going to scan up your handwritten work to an assignment. It's not there yet, but it will be created. Like a homework assignment, you'll scan it up there. So when you do so, make sure that you are using paper that I can read. Use green engineering paper, because when you scan it, all the green and all the grids disappear and I can read your work. Do not use college ruled paper. Do not use white and blue grid paper that you grabbed from work. Do not write on the back of your engineering paper, because I can't read it on the back side. Okay, is everybody hearing me on this? It is to your advantage that I can read it. Use if you're one of these people that uses a diamond tipped graphite pencil and writes microscopically, don't do that, because I can't read it. Use a soft lead that is nice and dark, or a pen, or you can use, some of you are submitting your homeworks on like a laptop generated grid. That's totally fine. If you've been doing your homeworks like on a laptop generated grid paper that's really easy to read, that's super cool. But if you're using a pencil and a paper, use engineering paper only. Yes.
So we can use that one on the exam, you said, for when we're using iPad for lectures?
Yeah, you can turn in your handwork that way. Yes.
Okay, because last time for mechanics of material, remember, you want us to use pen and paper.
Did I?
Yeah. Yeah, always take a picture of my exam.
Okay. No, I'm okay with that. You're not using your laptop to Google answers or communicate with anybody else. You're just using it to generate some hand calcs, like some of you are already doing on your homeworks, and that's okay. Again, where it crosses the line is if you're using the laptop to research the answers. Obviously, that would be crossing the line.
Okay.
Okay, so I've been doing a lot of talking. I'm sure you guys have questions about what to expect on Thursday.
Is it 3 questions?
Of course. You took my class before. You know how I do it.
Yeah.
You can either reassure your classmates, or you can scare the crap out of them. Just kidding. It's very straightforward. Yes, the book is okay to use for the tables. The book is actually okay to use for anything. This is an open book exam. You can have the book in front of you freely. You can use the book to look up equations or whatever. It is open book, but that's it. You're only supposed to have your book, your 1 page of notes, your pencil, your paper, and your calculator. That's it. If you're using the laptop to generate the hand calcs, then you can have the laptop there to generate the hand calcs. Obviously, you got to have some kind of computer in front of you to take the test. I understand that, but what's on your desk is just your book and your pencil and your paper and your calculator. Okay, who else? I
You know
want to, go ahead,
how many
please.
you know how many questions we're having?
Yes, I do. 3.
How much,
There's
how much time?
3 problems, and
Three
then there's
problems?
going to be a 4th question that has some kind of fill in the blank type questions. Okay, so there's 4 questions. 3 of them are problems like you'd see on a homework, and the 4th one is fill in the blanks.
Okay. How much time would you suggest, like, on each problem? Like,
That's a very good question. That's an excellent question. Most students finish my exams right about at the allotted time. You know, some quicker, some struggle a little bit to finish in time, but it's right about 2 hours is what it takes to do this exam with comfort and checking your answers and going back or looking up something in your book, that sort of thing. But probably the most important hint or advice I can give you is exactly what you just asked. There's 4 questions. 3 of them are problems. The 4th one is just fill in the blank. So the 4th one should not take you nearly as much time as the other 3. You need to control your time. You need to manage your time. And what I mean by that, even though I save this, I give this speech every single time. And every single time somebody spends an hour and 45 minutes on problem 1 and then realizes they have 10 minutes left to finish the exam and gives me nothing on problems 2 or 3. Each question is weighted a little bit different, but basically each question is a 50-point exam and each question is going to be 20 or 15 or 10. They're weighted differently. But the point is, if you spent all of your time on one question, the most you can possibly get on this exam is 20 out of 50. See what I'm saying? But if you gave me 75% on all 4 problems, you could still get 75% of the exam. So you have to manage your time. You have to watch your time. You have to say, okay, I'm starting at 5 o'clock. And at 5:30, I'm moving on to the next problem, whether I'm finished or not. And you got to give every problem a fair share of your time. And then if you have leftover time, go back and finish whatever you didn't finish. But it is far, far better to give me a 75% effort on all problems, assuming you don't have enough time to do the whole thing. Give me 75% on all problems rather than 95% on one problem and nothing to the others. That's a guaranteed way to not make it. Do we still get points even if we do not get to an answer? You might get some points. If you've started the problem and you've gone through the steps, but you ran out of time and you couldn't give me the final answer, clearly you won't get all your points, but you'll still get way more points than if you had not attempted it at all. Okay, I have a private question that requires Mr. Private Question Asker. Why don't we wait until we're basically done and then you can hit me up on your specific question if you like. Okay, do I have any more midterm questions?
Hey, Professor, just wanted to ask too, how lenient are you going to be on like partial credit, for example, if like, we use the wrong depth value and stuff like that and like arrive at a slightly different value than what is expected?
Hopefully I will answer your question by saying that I really put in an effort to find where the mistake was made. And if the mistake was made, I try not to penalize every step after that. So in other words, if, just for instance, let's say it's a design problem and I want you to design a beam for 1,000 kip feet and you calculate the moment and your answer for the moment is 500 kip feet. Clearly, everything you do after that's going to be wrong because you're only using half the load that everybody else is using. But I really tried to say, oh, he messed up on the load. It was supposed to be 1,000. He gave me 500, minus 2 points right there. And then I follow it through. And if you made another independent mistake after that, well, then I take off some points for that. But I don't penalize every single step from that point down because you're using the wrong beginning number at the very beginning of the problem. Does that make sense?
Okay, sounds good. Thank you.
Sure. And I try to do that. Okay, Eric's question is not for me. I have a private question. To the private question asker, an example of a blank question, an example would be, I'm just making one up. If I said allowable shear capacity, the blank would be VVN, would be the answer to allowable shear capacity is VVN. So you would fill in the blank with VVN. The spacing of two rows, one with 5 bars and one with 6 bars, the spacing of the rows is the same. But calculating D is not to the center between those two rows anymore. D has to be calculated because D is from the top of the concrete to the center of gravity of the steel. And you would actually have to calculate instead of eyeballing where the center of the steel is. So that's what I meant by that. Okay, anybody else? Okay, I have one student who private messaged me a question. I'd like to talk to that student. And then I have another student that I private messaged at the very beginning of this lecture. To that student, please stay on as well so I can talk to you. And if there are no other questions, then for everybody else, I will conclude this lecture and we'll see you at the test on Thursday.
Thank you. Have a good one.
You too.
Professor, before you talk to the private students,
Yes.
so when every time well, since we've been working from home, every time I scan and upload my work.
Yeah.
For some reason, it takes a while. So my professors told me to like anytime I'm gonna take an exam to let the professor know. That way, like I don't get any points deducted or anything like that.
I see. Okay. Well,
Yeah.
I basically allow like 15 to 20 minutes after the exam has been submitted. So if you start at 5 and you finish, again, I got to look it up. I think it's 7:05 actually. But if you finish or it finishes it for you at 7:05, then you have until about 7:20, 7:25 to get that stuff uploaded.
Okay. Yeah, what I usually do is I take pictures and then the iPhone tells you what time they were taken, just in case, like, you need proof and if
I see.
worst case scenario.
Okay. Okay, that's fine.
Thank you.
You're welcome. Sure, no problem.
Thank you, Professor.
Thank you.